Welcome back. In the previous class we started module 1 wherein we discussed topics from optoelectronic devices. We discussed the working of a photodiode, light emitting diode and an optocoupler. So to continue, we have three more chapters to be discussed under module 1, and the second chapter we deal with what is called as BJT biasing. So today's class we will revisit what a bipolar junction transistor is, what you have studied in your basic electronics. We will try to brush up for a few minutes. Before we start with what is BJT biasing and what are the different biasing circuits we have with the bipolar junction transistor. And to start with, a BJT stands for is a bipolar junction transistor. So when I say bipolar junction transistor, the charge carriers are both holes and electrons. So that is why we give the name bipolar. So when I say bipolar junction transistor, the charge carriers happens to be both holes and electrons. So based on the construction, we have two types of bipolar junction transistor. We have an NPN and a PNP transistor. You just try to recall these things which we have already discussed, we have already studied in your basic electronics. So based on how it is constructed, we have NPN and PNP transistor. Coming to an NPN transistor, you can see a P layer is sandwiched between two N layers, and in a PNP transistor an N semiconductor layer is transmitted between two PN layers. So you have something like this: P sandwiched between two N layers and an N sandwiched between two P layers to form a PNP or an NPN transistor. And BJT is a 3-terminal device. We have 3 terminals drawn, and the terminal drawn from the center we call it as base, one which is heavily doped we call it as emitter, and the other one is collector. Likewise, this happens to be base, emitter and collector. So these things you have already discussed. And coming to the symbolic representation, a PNP transistor is NPN transistor is indicated using this symbol. The arrow it indicates the flow of current. So the current always flows into the out of the emitter terminal. So we indicate it with this arrow. So this is a symbolic representation of an NPN transistor. And coming to a PNP transistor, so this is a symbolic representation of a PNP transistor. And out of the two types of transistor, NPN is widely used compared to your PNP transistors. So because of the stability it provides, and we prefer NPN transistor over PNP transistor. And coming to the different ways of connecting these transistors, because we have 3 terminals and we need to connect, we need 2 terminals to connect the input and 2 terminals to connect the output. So what we do here is we keep one of the terminals common. So accordingly we have common collector configuration, common base configuration and common emitter configuration. Because we are supposed to connect the input and output, we need 2 terminals, and because we have 3 terminals here, we will keep one of the terminals common to both input and output, and accordingly we have 3 types of configuration: common collector, common base and common emitter. So as I said, out of the 2 transistors NPN and PNP, NPN is widely used because the majority carriers here are electrons, so which are faster than the holes. So we prefer NPN over PNP. And coming to the 3 types of configuration, if collector is held common between the input and output, we call it as common collector. If base is held common between input and output, we call it as common base. And on the other hand, if emitter is held common between input and output, if input is applied between base emitter and output is taken between collector and emitter, keeping emitter common, we call such configuration as common emitter configuration. And out of the 3 configuration, we make use of common emitter configuration. Why common emitter configuration is widely used? Because of the advantage it provides. So, it has the advantage of having moderate input and output impedance. So, that is the reason we go with common emitter configuration compared to common collector and common base configuration. So, for henceforth for all our discussion, we try to keep an NPN transistor and a common emitter configuration. We discuss with respect to NPN transistor and common emitter transistor. Now, we will see what biasing is and what are the different types of biasing available with the transistor. So, just this was a quick recap, brushing of whatever we had already studied in our basic electronics. We know what a BJT is. BJT is a bipolar junction transistor which has 3 terminals, emitter, base and collector. Based on the construction, we have an NPN and PNP. Out of the two, NPN is widely used. This is the symbolic representations of NPN and PNP transistor. And how do we connect them? So, we can keep the collector common, we can keep the base common or emitter common. So, if and out of the 3 configuration, common emitter is used because it has moderate input as well as output impedance. Now, we will see what biasing is, what is the operating point before we take up the different biasing circuits. So, if you can recall, your transistor, applications of your transistor is as a switch, it can be used as an amplifier. So, for because we have 2 junctions, we should see to it that we have different ways of biasing these junctions. Either both the junctions are forward biased, or either one of the junction is forward biased keeping the other in reverse bias, or both are reverse biased. When both the junctions, input junction as well as output junction is reverse bias, the transistor is not conducting and we say it is operating in a cutoff region. So, input junction, output junction both are reverse bias, the transistor does not conduct and we say it is in cutoff region. And if both the region, both the junctions, input junction as well as output junction is forward bias, the transistor is said to be in saturation region and it acts as a it acts as a closed switch. So, when both are in cutoff region, it acts as an open switch, it does not conduct, and when both the junctions are, both the junctions, input junction and the output junctions, they are forward biased, they operate in what is called a saturation and they act as a closed switch. So, for your switching application, you use the transistor, you switch the transistor between the saturation and cutoff region to close the for the transistor to be used as a closed switch or an open switch. And one of the applications of your transistor is as an amplifier. So, what is an amplifier? Amplifier is a circuit which amplifies the input signal. So, the signal strength is input current, it is a current amplifier. Whatever current whatever the input current we have, it is amplified by a suitable level depending on the circuit parameters. So, for your amplifier circuit, you should see to it that your transistor is in the active region. So, when do I say it is in active region? So, if the input junction is forward biased and output junction is reverse biased, we call it as an active region. So, for faithful amplification, so for your amplifier to provide faithful amplification, you should see to it that the transistor is operating in the active region. And for keeping your active transistor in active region, we should meet certain conditions. So, on applying the DC biasing voltage to keep your transistor in active region so as to enable faithful activation, faithful amplification is called as biasing. So, transistor has wide range of applications, it is used as switch. So, when I want it to be used as switch, I want it to switch between open position and a closed position. So, if you are operating your transistor in cutoff region, it acts as open switch, and if you are operating your transistor in saturation region, it acts as a closed switch. And one more application of your transistor is an amplifier. So, if at all you want your transistor to be operated as an amplifier, you should see to it that it is active region. And applying suitable DC voltage along with other circuit components to keep your transistor in the active region. We call it as biasing. So, biasing is a process of applying DC voltage with other circuit components in order to keep your transistor in active region, so that faithful amplification is done, is called as transistor biasing. And we need to operate it at an optimum operating point, so as to see to it that the transistor is operating in its active region. At this point, let me introduce a term called as operating point. So, if you can see the output characteristics of your transistor, what is the output characteristic? Output current versus output voltage, we call it as output characteristics. So, we have output current on the y axis and output voltage on the x axis, and the plot of output voltage versus output current for different values of input current. So, it is basically in current amplifier. Based on the input current, the output is suitably amplified. So, this we call it as the output characteristics, and if it is reverse biased, we call it as in the cutoff region, and it is both are forward biased, we say it is in saturation region, keeping the which is suitably selected if you are using your transistor as a switch, and all these region we call it as active region. So, now I need to decide which is that operating point Q which gives faithful amplification. In the entire active region, I need to determine one operating point for which faithful amplification is done, and this point in the middle of your active region where faithful amplification is obtained, we call it as Q point, quiescent point, or we call it as the operating point. So, in the operating regions at the around the center, we determine the Q point wherein faithful amplification is done, and this point we term it as Q point or operating point or Q point or quiescent point. And what are the parameters that are to be considered, what are the factors that are to be considered in order to keep your transistor in active region, or what are the factors which are to be considered for optimal selection of your Q point, we will discuss now. So, as I said, Q point is the point on the center of your active region where faithful amplification is done, and what are the factors which are to be considered in determining the Q point, we will try to discuss. And we have 4 points which influence the selection of a Q point, and the very first point is you should see to it that your input junction, because I am talking it with respect to common emitter. So, what is common emitter configuration? If as an emitter is held common between the input and output, we call it as common emitter configuration, something like this. So, if input is applied between base and emitter and output is taken between collector and emitter, we call it as common emitter configuration. So, here I am applying input and output I am taking between the collector and emitter. Because emitter is held common between the input and output, we call it as common emitter configuration. So, all our discussion I limit to common emitter configuration because of the advantage common emitter configuration provides, which we have shortly discussed. Now, what we need to do is we need to see what should be considered in order to keep our transistor in the active region. So, essentially your input junction should be forward biased and your output junction should be reverse biased to keep it in the active region. So, with respect to common emitter configuration, the base emitter junction should be forward biased, while the collector emitter junction should be reverse biased. So, this is the very first condition which is to be taken, base emitter should be forward biased and collector base junction should be reverse biased. So, you should see to it that base emitter is forward biased and collector base junction is reverse biased. This is your you should see to it that this is satisfied. So, in order to keep your base emitter junction forward biased, what is forward biased? When positive is connected to positive terminal and negative is connected to negative terminal, we call it as forward biased. So, in order to keep your base emitter junction forward biased, you should see to it that it should be greater than the cut-in voltage. And cut-in voltage for if it is a silicon transistor, if it is a germanium transistor, the cut-in voltage is 0.3 volts for germanium and 0.7 volts for silicon transistors. So, you should always see to it that the base emitter junction is greater than 0.3 and it is greater than 0.7 volts for your silicon transistor. And the second one is the saturation current collector emitter voltage should not fall below the knee voltage. So, you should ensure VCE does not fall below what is called as knee voltage. And again, so for your germanium transistors, it is 0.5 volts, and for your silicon transistors, it is 1 volts. So, you should see to it that your collector emitter voltage does not fall below the knee voltage. It is 0.5 for germanium and 1 for silicon. Along with this, you should always see to it that there is some amount of current always flowing in the collector current, and this collector current which is to be maintained when no signal is applied to your circuit should be equal to the maximum collector current due to signal alone. So, you should see to it that collector current equal to the maximum collector current due to signal alone is always maintained. So, you should see to it that the collector current in the circuit is always equal to the maximum collector current which would be in the collector due to signal alone. Without any bias, when you apply signal alone, there is some current collector current flowing in the collector, and you should see to it that always collector current is equal to this value. And apart from this, very important is you should see to it that your transistor maximum ratings are not exceeded. You should see to it that the maximum collector current, IC max, power max, maximum power dissipated in the transistor, and also VCE max, that is collector emitter voltage, does not exceed. So, once if these power ratings are exceeded, there are chances of burning your transistor. So, you should ensure that the maximum current and power voltage ratings are not exceeded. So, efficient selection of operating point is done by considering these factors. You should ensure emitter base junction is forward biased and collector base junction is reverse biased. Along with that, you for doing so, you should see to it that emitter base junction is to keep emitter base junction forward biased, it should be more than cut-in voltage, and it is 0.3 for germanium and 0.7 for silicon. Along with this, you should ensure collector emitter voltage does not fall below the knee voltage, which is 0.5 for germanium and 1 for silicon, and some amount of current is to be maintained always in the circuit, and that is the maximum current which would flow in the circuit in the presence of signal alone. And along with that, you should see to it that maximum current, power and voltage ratings are not exceeded. So, keeping these factors into consideration, you decide an optimal operating point on the active region, and it is usually, as if you can just recall whatever we just wrote, this is your output characteristics. It is usually in the middle of the output characteristics. So, it is usually in the middle. So, this does not, this is in the cutoff region, and if you take a point here, it exceeds maximum power rating, it is near to the power rating, slight of variation would would violate this condition. So, optimal you select this as the operating point, that is center of your active region. So, with this we will see what are the different biasing circuits available in order to keep your transistor in the active region. So, with this quick recap, we will discuss the different types of biasing circuits available with the transistor, BJT transistors. So, BJT biasing, as I said, it is applying the DC voltage along with other circuit parameters to ensure the circuit is in active region. So, we need to decide an optimal operating point which keeps the transistor in active region, and for this we have 3 biasing circuits: fixed bias or self bias circuit, fixed bias or what is called as base bias circuit. Next we have is collector to base bias, and finally we have voltage divider bias. Along with this you have what is called as self bias. There is no mention in the syllabus. We will just fix to whatever is there in your prescribed textbook. We have fixed bias and or it is also called as base bias. Next we have is collector to base bias and voltage divider bias. Each one has its own advantage and disadvantage, and if you can at the end of the discussion you will get to know that of all the 3 biasing circuit, this offers maximum stability and it is widely used. So, we will take up each one of them. We will see what a fixed bias circuit is. We do all the analysis. We will take up few problems on fixed bias, and we will discuss the limitations and advantage of the first biasing circuit. Then take up collector to base bias. We will draw the collector to base bias circuit, do the analysis and discuss its limitations, and then we will take a voltage divider bias and see what a voltage divider bias is and how are the different. There are 2 methods of analyzing voltage divider bias, that is approximate method and accurate method. We will discuss both the methods and see and work out few problems on all voltage divider bias as well. In today's class we will try to discuss what fixed bias or base bias circuit is and collector to base bias circuit is, and try to work out few problems on this. Your fixed bias or base bias circuit happens to be the simplest of all the biasing circuits. So, it has minimal components, and we will try to see our what a fixed bias or base bias circuit is, do the analysis and try to work out few problems on this. So, your fixed bias circuit is something like this. As I said, I will be considering an NPN transistor and that too in common emitter configuration. It is the simplest of all the biasing circuit with minimal components. So, this is your fixed bias circuit. As I said, it has only 3 components. It has a supply and it has a base resistance RB and RC. So, as we are already aware, we need to keep the base emitter junction forward biased and collector base junction should be reverse biased, and to ensure the base emitter junction is forward biased, we bias it through VCC and RB, and collector base junction is reverse biased through VCC using voltage supply VCC and RC. So, here we have 2 coupling capacitors CI to couple the input AC signal to your circuit, amplifier circuit, and C naught as the output coupling capacitor to take out the output AC signal from the transistor to the output. So we need to do the analysis of this, and the analysis of the circuit in presence of DC alone, we call it as DC analysis. So we want to analyze the behavior of the circuit, that is we need to determine the operating point, we need to do the load line analysis, and for this what we need to do is we need to remove all the AC signal and analyze the circuit in the presence of DC alone. So what I do is I remove this input AC signal and remove the output AC signal, and now we will try to analyze the circuit. So this particular circuit analysis, we call it as DC analysis, and what we are to do here is we need to define the operating point. So what do you mean by operating point? We need to determine a point on the output characteristics wherein we have the faithful amplification. So for this what I do, if you can recall, what is your output characteristics? It is output current versus output voltage. So output current here is IC, collector current is your output current. So it is usually in milliamps, and the output voltage is VCE in volts, and we take this for different values of your input current. And input current, what is your input current? IB is your input current, and IC happens to be your output current. And we have here, in order to keep it in forward bias, we need to overcome the cut-in voltage VBE, and here we also have voltage between the collector emitter, we will call it as VCE. So what we need to we need to see to it that your collector emitter, emitter based junction is forward biased, and collector based junction is reverse biased, and the plot of output current versus output voltage for different values of base current, we call it as say IB is some 20 micro, 40 micro, 30 micro, and so on. We go on increasing the base current. This is a plot. Now my intention is to determine a Q point, optimal Q point on the output characteristics, which determines the faithful amplification. And when I say Q point, what should I locate? I should locate the corresponding IC, I will call it as ICQ, and corresponding output voltage VCEQ. So when I say DC analysis, I analyze the circuit in order to determine the Q point, that is I want to come up with an expression for IC, and I want to come up with an expression for VCE. So this is what a DC analysis means. So what I do, I will start analyzing the circuit, and as I said, your transistor is an amplifier. So what do you mean by amplifier? The output current IC is amplified form of your input current. So we are multiplying the input current with some gain to get the output current. So for that we need to determine IB. Once I have IB, I multiply it with the gain to get IC. So what I do here is I apply KVL to the input junction, arrive at an expression for IB, and then apply KVL to output junction, arrive at an expression for VCE, substitute the value of IB here, and substitute the value of IB in the expression. IC is equal to beta into IB, where beta is the current gain, in order to get the expression for output current, and subsequently substitute the value of IC in the expression for VCE to determine VCE. So this is how we do the analysis. So what I do here is, you are aware what is base emitter junction, base emitter voltage? It is the differential voltage between base and emitter. I can call it as VB minus V. Similarly, what is collector emitter voltage? Again, it is a differential voltage between the collector terminal and the emitter terminal. We can call it as VC minus V. So this is with respect to base emitter voltage and collector emitter voltage. Now what I try to do here is, I apply KVL to input junction, that is base emitter junction. So apply junction or base emitter. So when I apply KVL, what is KVL? Kirchhoff's voltage law. This try to recall your electricals, Kirchhoff's voltage law, which you have studied in your electrical first year electrical subject. So what does KVL state? KVL, according to KVL, in a loop, the algebraic sum of all the potential sources plus the voltage drops is always 0. So we need to go across the loop, see what are all the voltage drops, take their algebraic sum plus all the EMFs or electromotive force present in the loop, and those two sum up to a 0. So what I do, I apply it to apply KVL to your base emitter junction. What do you find? You find VCC, and this is IB. And what is voltage drop? Product of current and resistance along the loop is called as voltage drop. So your current is IB and RB, because when I pass through the loop, if direction of current and the loop they are in the same direction, we are taking it as negative. So it becomes minus IB RB. And when it comes to here, you have a cut-in voltage which is against the loop, minus VBE is equal to 0. Now what am I supposed to determine? I am supposed to determine the expression for IB. So IB, what happens? IB goes to becomes VCC minus VBE by RB. So this is the expression for the base current. And your cut-in voltage is what? It is 0.3 volts for germanium and 0.7 volts for silicon. So it is very negligible when compared to VCC. VCC could be 15 volts, 18 volts or 20 volts, your bias voltage. So you can often ignore VBE. Since VBE is very less than VCC, we could ignore this. Now what is IC? IC is what? Output current is always gain, current gain beta into input current. So because it is an amplifier, the output current is amplified version of input current. It is gain into input current. So gain into input current. So if you substitute, IC becomes beta into VCC minus VBE by RB. So and if you ignore VBE, if you neglect VBE, because it is very small, it is of range 0.3 or 0.7 volts when compared to VCC, which could be 20, 15 or so on, depending on your supply voltage. So this expression IC reduces to beta into VCC by RB. If you are ignoring, or otherwise you fix to this particular equation. Now what am I am done with determining on the output characteristics. What am I done? I am done with determining IC. Now I need to determine the corresponding value of VCE. So what am I supposed to do? The next point is determining VCE. So analysis or determining the operating point involves determining IC as well as VCE. How do you determine IC? For determine IC is given by beta into IB. In order to determine beta into IB, I want the value of IB. So what I do? I apply KVL to input section, get the expression for IB, substitute here, I get the expression for IC. Now I need to find the expression for VCE. Where do you find VCE? VCE you find it at the output loop. What we do? We apply KVL to the output loop and arrive at an expression for VCE. So I continue. So what is that we got for expression for IC? I will just write it here. IC is what is IC? IC is VCC minus VBE, sorry, beta into VCC minus VBE by RB. Or you ignore VBE, it is going to be IC is beta into VCC by RB. So now we will try to see we will try to find the expression for VCE. So for this, what we do is we apply KVL to output junction. So it becomes VCC is the power supply minus IC RC minus VCE is equal to 0. So, what we do? We want VCE. VCE is going to be VCC minus IC. So, this is the expression for collector current, output current, and this is the expression for output voltage. With this, we will try to discuss what DC load line and optimal operating point is. Now that you know, I will just drop this also. So, we know because I have just mentioned what output characteristics is a couple of times. What is output characteristics? It is plot of output current versus output voltage for different values of input current. In this case, in collector emitter configuration, the output current is IC, which is usually in milliamps range, and the output voltage is VCE, which is usually in volts. And we plot the characteristics for different values of input current. Say IB is some microamps. Usually the current input current is in microamp range, and because of amplification, if your amplification is 100 times, the output tends to be in milliamp range. So, IB say 40, IB say 60, IB say so. Now, I need to determine a point, an operating point. I need to determine an operating point on this active region where faithful amplification is done. And before that, we will introduce what is called as load line, DC load line. So, load line is a line which connects a point on your x axis to a point on your y axis. This we call it as a load line. So, to determine load line, what should we do? We should locate a point on y axis, we need to locate a point on x axis, join these two, that is going to give you a load line. So, in order to locate a point on y axis, what should be your value? VCE should be 0. So, when I make VCE 0, I locate a point on y axis. Similarly, if I want to locate a point on x axis, your current should be made 0. So, IC is 0, I locate a point on x axis. Now, I join these 2 points to get the load line. So, what is the expression which relates your output current and output voltage? This is the expression. So, we have VCE is equal to VCC minus ICRC, and this we obtained this expression by applying KVL to output junction. Now, if I want to determine a point on y axis, VCE should be 0. So, to locate point on y axis, substitute VCE is equal to 0. When I make VCE 0, what happens? 0 is equal to VCC minus ICRC. So, IC becomes VCC by RC. So, that is when VCE is equal to 0, we get a point on x axis, a point on y axis, which is corresponding to IC is equal to VCC by RC. So, I have located a point on y axis. Now, I need to locate a point on x axis. So, what I do? I make IC is equal to 0 in this expression. So, in this expression, substitute IC is equal to 0. What happens? Your VCE turns out to be VCC. So, this point we call it as VCC. And now, I connect these 2 points. So, this happens to be the load line, and the intersection of the load line with a point corresponding to IB, which is equal to this value, that is VCC minus VBE by RB, determines your quiescent point. So, this is your quiescent point, and the corresponding value of VCE we call it as VCEQ, and the corresponding value of IC we call it as ICQ. So, quiescent point as coordinates ICQ, x coordinate VCEQ and y coordinate ICQ. So, this is how I determine the operating point. So, in order to determine the operating point, you need to locate the LC line, the load line, and the point of intersection of load line with IB gives you the operating point. So, if you choose this as your operating point, or if you bias your circuit such that it gets VCEQ and ICEQ, the transistor does faithful amplification. This is what we mean. So, we will take up a few problems on this, and before we take up few problems, we will try to discuss the advantage and disadvantage of fixed bias circuit. Coming to the advantages of fixed bias circuit, the main advantage is it is very simple. Of all the biasing circuit, fixed biasing circuit happens to be the simplest biasing circuit, because it involves only a single power supply VC. Single power supply is the very main thing which is required for all the biasing circuit. Along with VCC, it requires only two components, RB and RC. So, this is simplest. That happens to be the greatest advantage of your fixed bias. And coming to the disadvantage, so compared to the next biasing circuits, that is collector to base and voltage divider bias circuit, the stability offered against temperature and variation in temperature and transistor gain is very poor. So, if you are operating if you are operating in an environment where there is a lot of variations in temperature and transistor gain, this is prone to get damaged. So, not suitable when your when your circuit involves a large variation in the transistor gain and the temperature. So, stability against variation in the temperature and transistor gain is very poor. So, this happens to be the drawback of your fixed bias circuit. Now, we will take up few problems before we go with collector to base bias circuit. So, we will try to work out few problems before we take up the next biasing circuit, that is collector to base biasing circuit. So, you are given with this problem and you are asked to determine IB, that is base current, IC, the output current, and VC. So, you are asked to determine all this. So, what is you can see, you can identify this as a fixed bias circuit with one power supply and two resistors, base resistor and a collector resistor. So, you already know the analysis of this. Now, we need to determine base current, collector current and VC. What is given? VCC. What is given? We will just try to list out what are all the parameters given. So, VCC is 18 volts. You are given with RB, and please note, in fixed bias circuit, the base resistance is in the range few hundreds of ohm, 100 kilo ohms, and your collector resistance is in a few kilo ohm range. So, this I just forgot to mention. So, in a fixed bias circuit, the base resistor is taken in the range of few hundred kilo ohms, and this is taken in the range of a few kilo ohms. Now, RB is given as RB is 470, and you are given with RC equal to 2.2 kilo ohm. Now, I need to determine, and you are also given with HFE. HF is nothing but current gain. which is beta is 100. Now I need to determine IB, IC and VCE. So how do you determine IB? Applying KVL to base junction, I get an expression for IB. IB you are already aware, it is VCC minus VBE by R. So we will assume, because if it is not given, usually they give you the cut-in voltage, base emitter cut-in voltage, or otherwise if it is not given, we will assume it is a silicon transistor and we will assume VBE is 0.7 volts, because usually we go with silicon transistors which has a cut-in voltage of 0.7, unless and until they don't mention, you can take it as 0.7 volts. So what is VCC? VCC is 18 minus 0.7 divided by RB is 470 kilo ohms into 10 power. So your base current is going to be, if you just compute this, you will get it as 36.8 microamps. Now I need to compute IC. What is IC? Output current, which is gain into input current, collector current. So gain is how much? Gain is given as 100 into 36.8 microamps. Micro is what? Into 10 power minus 6. You substitute this, you will get it as 36.8 milli. See the amplification, it has amplified your input current from microamp range to milliamp range. Now I need to determine VCE. So what is VCE? VCE is obtained by applying KVL to output section. So it is going to be VCC minus IC RC. So what is VCC? 18, and what is the calculated value of IC? It is 36.8. Micro is 10 power minus 3 into RC is 2.2 into 10 power 3. You substitute this, I have already calculated this for you, it is 9.9 volts. So we have determined VCE 9.9, IB is 36.8 microamps and IC is 36.8 milliamps. So you could be given a problem, you could be asked a question on analyzing the fixed bias circuit. You need to explain what a fixed bias circuit is, DC analysis, load line analysis, arrive at expression for output, the base current, output current and VCE, do the load line analysis. Or you could be given a problem and asked to find out, calculate the operating point, or indirectly IB, IC and VCE. So we will take few more problems on this. So we are given with one more problem here. So we are given a value of beta is equal to 100 and cut-in voltage VBE is 0.7 volts. You are asked to determine the operating point, Q point. So you are supposed to find the Q point and you are also asked to find the load line. So we need to find the Q point and the load line. So what we do, what do you mean by Q point? So we will just write on what are all the parameters given. So you are given with VCC is equal to 15 volts. You are given with RB is equal to 1 mega ohm. 1 mega ohm is 1 into 10 power 6 ohm. We are given with RC is equal to 4 kilo ohm.
which is 4 into 10 power 3. You are given with beta as 100 and VBE as 0.7 volts. Now what is to be determined? Q point is to be determined. When I say Q point is to be determined, what am I supposed to determine? I need to determine ICEQ and VCEQ. And along with this, I need to determine the load line. To determine the load line, we consider VCC is equal to VCC minus ICRC, and fix a point on x axis, fix a point on y axis, join this to get the load line. So to determine ICEQ and VCEQ, so what is IC? IC is beta into IB. So what is IB? Because it is a fixed bias circuit, beta is beta into VCC minus VBE by RB. Substitute the values. It is 100 into VCC is 15 minus 0.7 divided RB is 1 mega ohm, 10 power 6. So substitute this, you tend to get a value of IC equal to, I have already calculated this for you. So it is going to be 1.43 milliamps. Now I will determine VCE. So what is VCE? Is equal to VCC minus ICRC. So we have VCC equal to 15 volts minus IC, we have already found here 1.43 into 10 power minus 3 milli, and RC is 4 kilo ohm, 4 into 10 power 3. So substitute this, you will tend to get a VCE of 9.28 volts. So we have found out, I just write it here IC because I may need to use this later for plotting the load line, and VCE is 9.28 volts. Now I need to determine the load line. So what is the load line? Load line is a line which joins, which connects the point on x axis and y axis on your output characteristics. Just give me 2 minutes. 2 ನಿಮಿಷ. So your IC is the output characteristics, which is in milliamps, and VCE is the output voltage, which is in volt. Now I take it for different values of base current, and this is your output characteristics. So what should I do? I need to locate a point on x axis, I need to locate a point on y axis, join this to, this becomes a load line. And the point of intersection, we call it as Q point, which we have already determined, and the corresponding value is of current is 1.43 milliamps and 9.28 volts. Now what am I supposed to do? We have VCE, the output, the equation which relates your output voltage with output current is VCE is equal to VCC minus ICRC. So to determine the point on y axis, I take VCE is equal to 0, substitute VCE is equal to 0, I get IC is equal to VCC by RC. So what is VCC? 15 divided by RC is 4 kilo ohms, 4 into 10 power 3, and if you substitute these values, we get a value equal to 3.75 milliamps. So your current, this point is corresponding to 3.75 volts, and if you substitute to determine this point, I need to substitute IC is equal to 0. When I substitute IC is equal to 0, VCE becomes VCC, which is 15 volts, and this is here 15 volts. So this is connect these 2 points, and the point where it intersects with the point where the load line intersects your output characteristics, we call it as Q point, because we already know these values which we have computed earlier. This is going to be 1.43 milliamps and 9.28 volts. So this is how we have worked out 2 problems on fixed bias circuits. In the next class, we will work 1 or 2 more problems on fixed bias circuit and take up the next biasing circuit, collector to base bias, discuss its advantages and its disadvantage, and we will also discuss the voltage divider biasing circuits. With this we will be completing the one more BJT biasing chapter of your module 1.